Good morning, good afternoon. So thanks for the invitation. Here I will give a very quick overview of the gravity wave study and study their impact on the thermosphere and ionosphere. And an earlier version of this talk was given at AGU, and but there have been some updates. So here's an outline of the talk. I will mainly look at the gravity wave impact on the momentum budget and general circulation, their contribution to energetics, and their impact on the transport and the compositional structures, and the role of small scales, and all this they are related to wave flux. Then I'm going to look at the perturbation and their impact on the thermosphere, ionosphere, and a few challenges and future works at the end. So I think it's fair to say that the gravity wave theory, or at least the linear theory, is pretty well established since the 60s. And so I think the main challenge now is to study the whole system. It's really a very stiff multi-scale challenge. If we look at the wave scales, spatial scales, temporal scales, they're almost everywhere. They're very broad scale ranges. And also, I think it's safe to say that maybe for all global models, the smaller portion of the gravity wave spectrum is still a subgrid scale process. And on the other hand, even the smaller scales, they can still have very large, important contributions to the global budget. Another difficulty is that they have a global distribution. Their sources are tied to various meteorological sources, and which are highly variable in space and time. And also the media they are propagating through, the background atmosphere, wind, and temperature, they are also highly variable. And also the wave would feed back on those large-scale dynamics. And so there's a wave mean-flow interaction going on. I will maybe start from a little bit lower atmosphere. This is the stratosphere. I'll not go through the examples, but there have been intermodal comparisons both in the polar region on the left and equatorial region, showing that the importance of gravity waves and gravity wave forcing, in this case, the cold pole bias, especially in the south, due to the missing gravity waves. And on the right, you can see that without gravity wave or proper tuning of the gravity wave, the QBO signature cannot be reproduced in the equatorial stratosphere. So if we go a bit higher, there's this well-known temperature anomaly in the mesosphere, lower thermosphere. It is driven off equilibrium, radiative equilibrium. It's cold in the summer and warm in the winter time. And this anomaly region is usually coincide with the wind reversal, so which suggests a dynamical origin for this problem. And indeed, later studies found that it is the gravity wave driving that was causing dynamical cooling or heating in this region. And if we go further up, this is a simulation, controlled simulation of WACCM-X, two almost identical runs, zonal mean, zonal wind, and temperature. And but one is run with parameterized gravity wave forcing and one without. So you can see that with gravity wave forcing, you do see this jet reversal in the MLT region, Mesosphere, lower thermosphere. And also the temperature structure is better resolved. And if we look at the thermosphere, we know that the thermosphere circulation is primarily driven by the EUV heating, and you have the summer to winter circulation. But you can see, even though in these two cases the EUV heating are identical, you see that the wind can be quite different. For example, in northern summer hemisphere, you see that without a gravity wave driving the jet, the westward wind can be much stronger. than the case with, and also in the winter hemisphere is different. In the winter, we see more of an eastward flow rather than a westward flow. And the other kind of interesting dynamics is in the lower thermosphere, where above or in between the mesosphere summer to winter circulation and the thermosphere summer to winter circulation, generally, at least in the model, we see a return flow, which is also driven by gravity waves. And this circulation can be very important for the redistribution of species in that region. And but we must say that in the model, this is very poorly constrained, and definitely observation data will help us. And talking about that, this is a comparison of several different whole atmosphere models, actually 4 different models, showing that the importance of gravity wave and gravity wave forcing. So in all those 4 simulations, it is for a targeted period in 2009, and the model are nearly identical below about 50 kilometers due to constraints from reanalysis or data simulation. But the key point is that if we look at the mesosphere and thermosphere, they deviate quite significantly among the different models. And the analysis by Patatella et al. Showed that one of the main reasons for the models being different is the very different gravity wave driving from their respective parameterization schemes. So gravity wave parameterization seems to be necessary, but it's also a major source of model uncertainty and even model bias. And another thing is the gravity wave contribution to the energetics. So using these numbers as a reference, we know that the average daily energy input for solar EUV is 464 gigawatts, mainly from the solar forcing. And the Joule power is near 100 gigawatts. And of course, they are mainly distributed near the polar region, high latitude. And the particle kinetic power is about 1/3 of that. And recent years, there have been studies looking at the energy flux from below. And so this study by Becker, 2017, used a relatively coarse model to look at the energy deposition at various altitude. And at about 100 kilometers, they found that the deposition rate is about 35 gigawatts, and 75% are from gravity waves or parameterized gravity waves. And using a high resolution model, we also look at this, we look at the energy flux, not the deposition rate. So this is a flux at various different altitude and over 1 year. So you can see that at about 100 kilometers, it is 10 to the 2, it's about 100 gigawatts. So very comparable to the Joule power. But of course, the distribution can be quite different. And also, if we calculate the deposition rate, it's tens of gigawatts comparable to the parameterized study. And then the transport, we know that the mesosphere, lower thermosphere is a key region for controlling the mass exchange between the space and the atmosphere. And almost any motion there could induce a down gradient transport, therefore change the O2 and 2 ratio, and also the plasma density composition. So these are a few known pathways through large-scale circulation, the spoon effects, and the large-scale waves, tides, for example, and also small-scale motions like eddy mixing, which is a catch-all phrase for turbulence and gravity waves. And here I show an example of that dependence. This is a slightly earlier version of WACCM-X. It shows the WACCM-X results, MF2 WACCM-X results red compared with observations at both low latitude and the mid latitude. And you can see the model is really underestimating the MF2 compared with observations. And I think we now understand the cause of that. it is really due to incorrect implementation of the Eddy diffusion from gravity wave in the model. So the red curve is in the previous version of the model. This is a global averaged Eddy diffusion. And you can see that it keeps growing with altitude till it peak at about 200 kilometers, which physically kind of doesn't make sense because we know that the wave above the tropopause should dissipate very quickly. So if we add this constraint to the model, ramping down the Eddy diffusion coefficient, we'll get a much better global plasma density. This is the old case, and this is after reducing the Eddy diffusion in the thermosphere. So this really demonstrates the sensitivity of plasma density and composition to the transport in the lower thermosphere region. Another important thing is the small scales, which it's difficult to measure or model currently, but they could still be important. So here I show two model results. One is from the high resolution WACCM, the blue curve, and red is the WRF simulation, 4 kilometer resolution driven by WACCM. And these are the kinetic energy spectra, horizontal and vertical, and then momentum spectra. So what's interesting is that if we use high resolution models, we see that similar scaling extends all the way through the mesoscale range. And then also the vertical wind has a really flat spectrum, which means that the vertical fluxes would also have a very flat spectrum. What that implies is that for the momentum flux, for example, the small scale processes can contribute quite significantly to the total momentum budget. And then, so those are the wave fluxes, but the wave perturbation can also be very important. They can cause large wind and wind shears as they grow in altitude because of the decrease in density. So the wind shear can be very large in the mesosphere and lower thermosphere that can drive the ionospheric sporadic E layer. And also the large perturbations from the both primary and secondary gravity waves, they can force large TADs and TIDs, which can trigger or see the ionospheric irregularities. And unlike the fluxes, these effects cannot be parameterized. They must be resolved. So this is an example from a high resolution WACCM. Here shows 4 levels of vertical motion, vertical wind. One thing we can see from here is that in the thermosphere, lower thermosphere and mesosphere, the vertical wind is very large, can be twice as large as the maximum vertical wind seen in the tropopause region above the tropical cyclone. So very large motion in that region. And also, if we look at the horizontal wind, they can also be very strong. And I talked about the vertical shear, the vertical wind shear. We know from rocket measurements that we have this very large prominent peak between 100 and 110 kilometers. And previous model cannot really resolve this, but using high resolution model, we start to capture the structure at the right altitude, right above the mesopause, and at various latitude. So, so very significant peak. And if we look at the structure, the spatial structure, longitude and height, we see that a lot of this large shears are associated with quite coherent spatial structures, likely gravity waves. So this way, this large shears, as I mentioned earlier, can be very significant and important for things like a sporadic E layer. And then recently we have tried to push also WACCM-X to higher resolution. We haven't reached the like 25 kilometer resolution, as I mentioned earlier. We haven't got there yet. We're working toward that. The current resolution for WACCM-X is about ½ degrees or 60 kilometers. And so these are short runs for 2 cases. One is at equinox under solar min conditions. The other is July under solar max conditions. If you look at, and this altitude is at 130 kilometers, E region. So if you look at the similarity or difference, maybe the main difference would be the magnitude. The vertical wind seems to be a little bit smaller under especially the winter hemisphere. The summer hemisphere, when the solar activity is high, because of most likely the larger molecular dissipation in that season. And then we can feed this the neutral motions to SEMI3, and Joe Huber run a SEMI3 model that is 1 week coupled to WACCM-X, and under the solstice, equinox and solar min conditions, he was able to get quite realistic looking irregularity or bubble structures in the equatorial region after sunset. And this comparable quite well with the structures seen in gold. And interestingly, if we look at the solar max simulation, there's no such a bubble. So it's quite consistent with the climatology, the seasonal climatology of the bubbles. So as I mentioned earlier, or described in the previous slides, there are maybe at least 2 kinds of challenges we need to address in future development. One is the large uncertainties in parameterizing gravity wave, especially various gravity wave fluxes. For that, we need to better specify the wave source and also the wave propagation. There are many issues in the current parameterization, and also the wave impact, especially the impact for thermosphere and ionosphere, the impact of the waves in a highly dissipated environment, which current parameterization usually does not really consider. And the other development path is to develop high-resolution whole atmosphere models, and that is clearly needed for studying the effects of gravity wave disturbance, such as irregularities. And also, it's important for studying the in the thermosphere, ionosphere, mesoscale structures due to both the lower forcing and upper forcing and their role in the coupling. Another thing is to try to maintain a consistency when we push to higher resolutions between the resolved waves and the missing or parameterized gravity waves. And specific for maybe relevant for this mission, Daedalus mission, the gravity wave between 100 and 200 kilometers, very important. And mentioned a few examples. The impact on the thermosphere circulation, both lower thermosphere and upper thermosphere, can be very important. And just maybe first order estimate indicates that they could be important for the energetic contribution, and their spatial distribution, the vertical and horizontal, need to be better specified or studied. And also the transport can be very sensitive in controlling the thermosphere ionosphere composition. Also the spatial distribution, spatial scale, and the spectral structure, the magnitude can be both important for the flux studies and also the irregularity studies. And currently, I would say from the measurements, most of the measurement, whether ground-based or satellite, for gravity waves, neutral wind, temperature, and density, they're below 100 or 110 kilometers, with a few exceptions. So I think Daedalus will be a very welcome new addition to this suite of measurements for us to specify and capture all these quantities mentioned above. Thank you very much.
Thanks a lot, Hanli. That was a very impressive talk. Very interesting. Are there few short or 1 or 2 short questions to Hanli or comments from the audience? So if not, I have a very short question. So you showed when you entered in just 2 slides ago the gravity waves into SEMI3. As you already mentioned, that's a very nice coincidence with the observations from one season to the others. So do you think that it is the seasonal variation of the appearance of gravity waves that makes these bubbles growing or not, or is it other conditions?
In this study, we haven't looked at that. It seems maybe that's why Joe want to make two simulations to look at that. From here, as I mentioned, the vertical wind is somewhat weaker, but in general, you would say there's still plenty of waves in this case, in the solar max case. So maybe seeding, gravity wave seeding is one aspect,
Okay.
but I think definitely the large scale dynamics and electrodynamics must play an important role here too.
Okay. Okay, so Sampat asked if there are any zonal movement of waves taken care efficiently in this height.
Sorry, the zonal movement?
Yes, zonal movement of waves taken care efficiently in this height.
Yeah, you mean whether the waves would propagate horizontally in the zonal direction?
Yes, that's a question in the chat by Sampat.
Okay. Yeah, I think we take some quick look at the animation of this events. Clearly, they are moving in the large, and they are the movement is kind of interesting. It's really it seems that they are trying to move, always try to move against the local tidal winds, the large scale tidal winds. But definitely, yes, there's a movement, horizontal movement or propagation of these waves.
Okay, thanks a lot, Hanli. Very
Sure.
nice talk. Very good. Thanks a lot.